reason. All right. Good evening. Well, thank you for the invitation to come and speak about Titan and Dragonfly. Um, it's a very exciting mission that is currently in its formulation phase, and I expect we will be starting our very long journey to Titan from Florida. First, just a note about APL, where I work, up the coast in Maryland. APL has a long history of building spacecraft. It developed the transit navigation satellites that was sort of the predecessor of GPS. We have got into the planetary business with the first discovery mission near the Near-Earth Asteroid Rendezvous back in the early 90s. We built Messenger, which it was orbiting the hottest planet, and in fact Parker Solar Probe, even closer to the sun than that. And of course, New Horizons visited Pluto and Arrokoth and is on its way into the outer reaches of space. So there's a lot going on here, and I'll tell you about Dragonfly. My own trajectory, I often like to share, just for the benefit of early career folks who wonder how these sort of opportunities emerge. I started out as an engineer. My formative years were in the UK, and I was very fortunate that my first job straight out of college was for the European Space Agency, working on the very beginning of the Huygens project, the Titan probe that was part of the NASA, ESA, ASI, Cassini mission. And in fact, I joined the project there at roughly the same stage that Dragonfly is in right now, the early part of Phase B. I went from the Netherlands, from ESA back to the UK. I sort of saw that I kind of was maybe a bit more of a scientist than an engineer, and I really enjoyed the thinking about how systems and instruments interact with planetary environments. And so I got to work building one of the experiments on the Huygens probe. After I got my PhD, I came to the US, to Arizona, to work on the first Hubble Space Telescope maps of Titan, and got involved in planning Cassini's radar observations. And partly because of that, I kind of picked up a bit of planetary geology. I sometimes appear on TV shows talking about Titan sand dunes or other landforms, but I don't actually have any formal training in geology. We also, as Cassini was on its way, started thinking about what we might do at Titan afterwards. And in 2006, I came here to APL, and as is the typical situation in this business, I was involved in many proposals that went nowhere. But I have been lucky to be involved in a number of flight missions. The Akatsuki mission, a Japanese climate orbiter at Venus, the InSight Mars lander, and in fact I have a small role in the Perseverance Mars rover about to land on Mars. Just what I see something flashing on the edge of the screen, because I can't really concentrate on the chat as well as talking. The hope is to defer questions to the end. We'll be able to come back to slides if we need to refer to them, but I'm sure questions will come up. So put them in the chat, or the Q&A rather, or there'll be an opportunity to ask them at the end. A human lifetime is sort of has an interesting relationship to the year on Titan, and Titan's year and seasons are an important part of this story. Saturn and Titan take about 30 Earth years to go around the sun, and so a season on Titan is 7 years, and so a human being basically gets to go around the block 2 and a bit times. And obviously the astrodynamics are such that something launched from Earth takes a quarter of a Titan year to get out to Saturn. So, this is not an enterprise for those seeking instant gratification. One important point to note about Saturn's orbit around the Sun is it's somewhat eccentric. The perihelion is an astronomical unit closer to the Sun than is aphelion. And the arrangement of Titan's poles, Titan has a tilted equator, much like the Earth, is such that the South Pole is kind of pointed towards the Sun during southern summer. So southern summer happens to be near perihelion. So southern summer is shorter, but warmer than the northern hemisphere. So the seasonal cycle isn't quite symmetric, and that turns out to affect how liquids are distributed on the surface of Titan. Titan not only has a dense atmosphere, but also has surface liquids. It's fun to put on life milestones on a Titan clock. You can put your wedding days and things like that on here. I can now populate a good part of the Titan year with books I've written. Some of these may be of interest to you. I did a book on the dynamics of spinning things like frisbees and boomerangs. There's a book on space systems failures. Several books on Titan, including this one, the Owner's Workshop Manual, which has all the best mosaics and results from Cassini. But it's interesting sort of looking back that all of these different dimensions all sort of converge in what we're trying to do with Dragonfly when you are thinking of exploring an area that has dunes, or you're interested in how rotor downwash may kick up dirt. The work I've done exploring sand dunes on Earth and Mars and Titan comes into play, and that to me is the sort of most stimulating aspect of the work I do. That it can be very multidisciplinary. Early on in the Dragonfly project, I served the role of project scientist, but because I have this sort of engineering background and for some other reasons, we sort of made up the term mission architect for what I do. It really is about understanding and anticipating how the vehicle and the instruments are going to operate in the environment on Titan and on its way there. Going back to Huygens, I was involved very early on, and in the development of one of the instruments. One of the fun things about the way the European Space Agency puts missions together is it has a sort of formalized pork barreling that contracts are distributed to the member states in the same proportion as ESA receives a budget. So, if you're a project manager and you just want to get the thing done, right, just have the Germans build the whole thing and it'll be great. But what a project manager in ESA has to do is give 20% to Germany and 25% to France, and 3% for Belgium, and find something for the Finns to do. So it's a real sort of political and industrial contractual jigsaw. And I like to point out that one of the reasons that space missions are challenging and expensive is you have to anticipate how to bring all this stuff together. Not only is there a heat shield here built with French ballistic missile thermal protection technology, but that is attaching to a back cover structure that was made in Spain. You need a dolly to hold the things in place while you line the bolts up, and lining up these bolts has to be done on paper. This was early 90s, before PDF documents, before Box or other document sharing websites. We faxed big documents around and mailed them, and those described the signal levels on the voltage, and the pins where the bolts go and so on. And then somebody had to figure out that to mate these things together, you need this dolly which comes from Austria, as it happens, and that has to fit through this door in this test facility in Germany. So there are, a lot of interesting things coming from different places to make Huygens happen. But it was a very bold endeavor. It was a completely new thing for ESA. It had never done a planetary mission before. It would have been a bold thing for NASA to do by itself, come to that. But it was a great adventure to be part of it from the early stages. And then we had to wait. It took 7 years from Florida to the Saturnian system. Cassini arrived in July of 2004 and delivered the Huygens probe actually Christmas Eve. And the probe sailed through space by itself for 3 weeks before hitting the Titan atmosphere at 6 kilometers a second and parachuting down to the surface. There was no actual guarantee that the probe would survive impact because we had no idea what we were going to land in. It was a bonus, in fact, that the probe survived quite happily. My own little 14 grams of the 200 kilogram Huygens probe is this thing. It's an instrument called a penetrometer. It's a little force transducer that stuck out of the bottom of the probe. It has a little piezoelectric element that generates a charge when it's squeezed. And so when the probe came into to land, to impact, this instrument was driven into the ground. And the force history tells you a little bit about the material that we would land in. So the thing is sampled at 10,000 samples a second. There were 500 readings, so 1/20th of a second, it's all over. This is a force axis, and dry sand. You're familiar with sand at the beach. When you squeeze it, the grains sort of lock up together, and so you get this sort of steeply increasing force signature. Wet clay deforms like a plastic solid or a very viscous liquid. It's more or less constant, and gravel gives you spikes, and the spacing and the height of the spikes tells you about the particle size. So very very simple, almost low tech sort of instrument. And when people can travel again, you can go and see this in the spare, at least, in the London Science Museum. And like all good scientific stories, what we actually got at Titan was nothing like the tests I did in the lab as a grad student. This is at the European Space Operations Center in Darmstadt, Germany, in January of 2005. And there is the data from Titan from this little instrument. First surprise was, wow, the thing actually worked. After 7 years waiting for this, 1/20th of a second of data. And you'd think, actually, having spent 7 years waiting and 3 or 4 years in development, that you'd get a few weeks to carefully consider the data and develop a scientific interpretation. But no, the data came down at 6 p.m. There were 80 of us scientists at ESOC, and about 150 journalists camped outside. And so we got the data at about 6 p.m. and press conference at 11. Go. So we all had our assigned tasks. Mine was to look at the little squiggly line and make sense of it. And well, what happened here? Well, all right, this bump is just the back end hitting, doesn't really mean much. Otherwise, it's kind of flat, little spiky here, and there's this big spike at the beginning. What was that all about? Was there a spark jump from the surface, or what happened? And we just sort of speculated. Well, it looks in terms of hardness, looks like packed snow, kind of clay, maybe wet sand, something like that. And well, I don't know about the spike. Maybe there was like a crust on top, and sort of said creme brulee. And hesitantly, my former advisor, the principal investigator of the surface experiment, offered that up at the press conference. And the media loved that, right? The public likes food analogies. Titan team gets just desserts from creme brulee surface was the headline in Nature. We hadn't, when we were developing these interpretations, seen the pictures. There was another team in another building working on those, but in fact, we had no right to get this to expect this picture The probe could have failed, the parachute could have fallen on top of the camera, but in fact we got this view showing these rounded cobbles. And the way you get rounded cobbles is by tumbling them in a stream, in a flash flood. And that told us instantly that Titan has been shaped by similar processes to those we have on Earth. There's a methane cycle on Titan, just as there is a hydrological cycle with water on Earth. Let me not to dwell too much on the past. I know everyone wants to hear about Dragonfly. So as the Huygens probe came down, it took images giving us very much a sort of airplane window view. This is from about 7 kilometers up, so typical airliner altitude. And we see this sort of highland. This is about 100 meters higher than the dark material. You can see sort of river networks here. And these two sort of straight streaks up here are actually sand dunes. We subsequently observed them in Cassini radar images and generalized to other parts of the planet where the dunes are very, very obvious. And you can see off in the distance, this is 20 odd kilometers away. The Titan atmosphere is hazy. And that's why the Voyager mission in the 1980s couldn't see the surface, but it's opaque because it's very thick. The haze content per unit volume is actually quite small. The visibility in terrestrial terms would be many tens of kilometers. So it's important to understand that. Titan is 10 times further from the sun than the Earth, so it gets 100 times less sunlight at the top of the atmosphere, and only some of the light filters through the haze. The blue light is blocked completely. Most of the light that gets through is in the red and the near infrared. There are wavelengths at which light is strongly absorbed by methane in the atmosphere. And you can tell I've got this transatlantic schizophrenia. Sometimes I say methane, sometimes I say methane, tomato. And it's important to understand this spectrum when you're designing cameras, for example, right? Your exposure time has to be long enough to get enough light to get a good signal. But on a moving vehicle like a rotorcraft, you have to think about, is the vehicle going to be vibrating? So you don't want too long an exposure time. But that has all been sort of demonstrated by Huygens. Huygens gave us the ground truth that validates these light models. And in fact, we'll use some of this absorption to measure the methane humidity as part of our efforts to understand Titan's weather. So just to put things in context, right, 1,000 times less sunlight, so 100 times less at the top of the atmosphere, 10% of that gets down to the ground. That's still 1,000 times brighter than full moonlight on the Earth. I mean, you'd be able to see completely fine. Your eyes adapt very easily. We know Titan has surface liquids. In fact, they're at around the North Pole. There are several seas and lakes. There's one or two lakes in the south. There are occasionally clouds. It's actually very rare that there are convective, cumulonimbus clouds that have rain on Titan. It does happen, and in fact, Cassini saw maybe 2 occasions where not only were there clouds, but there were surface changes. In 2009, the equinox season, we actually saw a big cloud system develop, and then areas of the ground that had been bright got dark, and then over the following months they brightened back to where they had been before. And the obvious interpretation is that the ground got wet, that makes ground darker, and then it dried out. So Titan has active weather today. I mean, it's seasonally dependent, but it's the only other world in the solar system where we know that liquid rains down onto the surface and carves river channels today, the same way that it happens on Earth. Except the working fluid here is methane at 94 Kelvin and not water. So it's a very interesting world to study from the perspective of comparative planetology. We know something about the winds on Titan. We actually now have very good models global circulation models that simulate the dynamics of the atmosphere, conditioned by the fact that the sun is absorbed by the haze at different altitudes. And Titan rotates slowly compared to the Earth. Titan goes around Saturn once every 16 Earth days. So a point on the surface of Titan is in darkness for 8 Earth days, which turns out to be important in our operations planning. The winds near the surface are about 1 meter per second. Titan's atmosphere, which is mostly nitrogen, is about 5 times denser than ours. So you get a bit more dynamic pressure, bit more effect for a given wind speed. But the winds are really quite gentle. Big enough on occasion to sculpt sand dunes, and probably to form waves on the surface of the seas, but not typically. Anyway, we can use this understanding to develop the sort of environmental specification for vehicles to explore Titan. And maybe I've gone into a bit more detail on this slide than I should. We can come back to it if anyone's really interested in turbulence. Let me just check that the audio is still working okay. And I'm not hearing anyone say so. Okay, great. No worries. Okay, I'll press on. So Cassini was at Saturn and Titan for 13 years, from 2004 till September 2017. It had a first extended mission, and then in fact a second extended mission to take it all the way to the northern summer solstice. And by making about 126 close flybys of Titan, Cassini was able to map much of its surface. This is a near-infrared image mosaic made from actually thousands and thousands of images. And you can see there's a very sort of diverse landscape. Titan's diameter is 5,000 kilometers, so it's bigger than the planet Mercury, rather bigger than our moon. And you can see there's bright areas and dark areas. This bright leading edge feature is called Xanadu. It's actually somewhat mountainous. You can see a couple of craters, but actually not many craters. The surface is geologically young. All these sort of wispy dark areas at low latitudes are actually sand seas covered in dunes. The high latitude dark areas, this sort of sprawling thing, is Kraken Mare, is a sea of liquid methane, about almost 1,000 kilometers from end to end. And there's another lake in the south. But something we really don't know very well, and knew even in the late 90s before Cassini was launched, we really don't know what the stuff is made of. I mean, we know there is photochemistry in Titan's atmosphere, wherein methane is broken up by ultraviolet light, and the fragments of methane and nitrogen recombine in all kinds of ways to make heavier organics that drizzle down onto the surface. But exactly what the composition is, and in particular, how that organic composition may have been further processed on Titan's surface in those places like impact craters, where there may have been energy delivered by the impact that has melted some of the crust. And we think the crust of most outer solar system satellites is water ice. So when you form a crater, you make liquid water, and you basically in the laboratory, if you add liquid water to Titan organics or simulations thereof, then you can make amino acids, which are the building blocks of proteins. You can make pyrimidine bases, which are the letters that encode information in our DNA. So you can make a lot of the building blocks of life, and we've no idea exactly how far down the sort of ladder of complexity, or up the ladder of complexity, towards the processes that execute the functions of life Titan may have got. But the results of this amazing chemistry experiment are littered around on Titan's surface, frozen solid, waiting for us to pick up. This is really driven what we want to do next, and shaped ideas, pre-Cassini and post-Cassini, to really understand just how biologically relevant the chemistry on Titan gets. We want to understand Titan's weather as well, how the methane cycle works, the dunes, the shape of dunes and the size of dunes actually records the past climate. We think Titan has climate cycles a little bit like the Kroll-Milankovitch cycles that drive our glacial periods. But on Titan, what happens is they actually push the liquid from the northern hemisphere and distill it over to the south and back again on 50,000 year timescales, we think. And of course, we are always have to keep an open mind to the possibility that deep in Titan's interior, there may be, we think there's a global water ocean. And there's even the possibility that some of the functions of living things could be executed in Titan's surface liquid, in a non-polar solvent. We don't have any good ideas about exactly how that could happen, but we don't know enough to rule it out. And so one has to keep that in mind for exploration. So there were ideas even in the 1990s. Titan's got a thick atmosphere, so could you fly a balloon? Sure. You can also use that dense atmosphere to deliver a lot more hardware into orbit than you can at an airless world like Europa, for example. If you use air capture to slow down, you don't need the same rocket propulsion to break into orbit, and so you can deliver a much more capable vehicle. Those ideas were kicked around in the 90s and early 2000s. The question arose, however, how can you access the surface material with a balloon? It's a great aesthetically pleasing way to get around, but you don't have much control authority, and interaction with the surface presents some challenges. There were ideas about airships as well, and they mitigate some of those considerations, but only to an extent. Here at APL, we were tasked by NASA in 2007 to sort of look at what would we want to do at Titan after Cassini, and there's many things that can be done from orbit. The radar map from Cassini, for example, only covers about 40–50% of the body, and topography data is much more sparse than that. Obviously, Titan's atmospheric chemistry has seasonal changes. There's all kinds of things that even Cassini's instrumentation could have done much more extensively if Cassini had been in orbit around Titan. But because it only flew by Titan once in a while, it just had these sort of fleeting snapshots. So a Titan orbiter would give amazing science, and you could also improve the amount of data you get from surface platforms by acting as a relay. We ventured a balloon as had been done before, and we also suggested a lander. A lander lets you do things like seismology to probe the interior and maybe see how deep that water ocean is. And of course, you can access the surface material and really diagnose its structure and composition. So those three elements were sort of the perfect shopping list, but they add up to an expensive multi-element mission. And Europa took the lead in the outer solar system flagship set. There were some smaller mission ideas that came along about a decade ago. There was the Titan Mare Explorer capsule, a capsule to splash down in one of Titan's northern seas. It would have been on its way right now if it had been selected to arrive before the end of northern summer. Northern summer lets you see the sun and the earth from the North Polar regions, and that lets you do direct to Earth communication. So you could do a mission within the very restricted cost envelope of the NASA Discovery program. There were even ideas about airplanes on Titan, ones that would never touch the ground, just keep flying, ad infinitum. Those relied on a particular power system that was not realized, at least not yet, however. Now, back in the late 90s, when I was thinking with colleagues at JPL about airships and so on, we were sort of confronted with the question of, where does an airship make sense? Where's the break point between heavier than air and lighter than air travel? And when you start looking into that quantitatively, you sort of realize that, wait, actually, the best way to explore Titan, if you're interested in accessing the surface, is with something like a helicopter, because you can spend most of your time sitting on the ground where you can do science, and you could just take off once in a while and relocate. So like having a lander that just lands at multiple places. And when you do the rotorcraft math, taking into account the denser atmosphere on Titan and the lower gravity, it takes about 40 times less power to hover a given sized vehicle on Titan than Earth. And there's even some additional benefits from the low temperatures. But I sort of proposed this Titan helicopter thing, and it got this garish cover on in New Scientist. But the pieces weren't there. This was sort of before its time. This was before the drone revolution. There was not the multi-mission radioisotope thermoelectric generator. There were just notional radioisotope power sources. Titan is too far from the sun for solar power to be effective, even especially on the surface. So the idea was there, but it was too early in 2000. But the pieces have emerged, as you know, when you see any airport gadget store, you can buy a little quadcopter for $20 and fly it around. We now have the multi-mission radioisotope thermoelectric generator. A second one is about to land on the Martian surface next week. In fact, I had the opportunity as my last trip before COVID clipped my wings, was actually out to the Idaho National Laboratory to see the MMRTG that's on Perseverance. I wanted to make some measurements about how the MMRTG affects the atmospheric electrical conductivity around it. The radiation causes a little bit of ionization, which actually affects some of the measurements that we plan to make with Dragonfly. I should stress that although Dragonfly's original design was proposed with the MMRTG, strictly the use of radioisotope power systems is subject to approval per the National Environmental Policy Act, and so there's some approval processes yet to be performed before that is sort of formally announced as our way forward. So the concept that I articulated back in 2000 and that we embrace for Dragonfly is really driven by the Titan day-night cycle. You are, if you're at low latitudes on Titan, then you are blocked from the sun and the Earth by Titan's interior. Earth and the sun are below the horizon. It's nighttime, it's dark, you can't communicate. So we just sit and we take the 80 watts, 90 watts, whatever comes out of the MMRTG, and we trickle charge a large battery. That's this blue curve charging up. And that gives us the energy that we need when we fly. We can only fly for half an hour or so, and that uses most of that battery energy. Even though it's 40 times less than Earth, it's still a lot of power. So we charge up, basically doing nothing except listening with our seismometer, monitoring the weather during the night, and then when the sun comes up, we downlink the data to the Earth. We check the weather. We get approval from ground control, and do our flight to a new place. And then once we land, we recharge the battery for 16 hours, and then we have an 8-hour downlink to the Earth. Charge up, downlink, charge up, downlink, and you can see we're slowly eating into the battery reserve, and until at sunset, where we have some comfortable margin, we just start charging up again. So this is much like the way rovers work on Mars, except instead of having a 24-hour cycle and having to be on Mars time, you can basically be 1 week on and then 1 week off. So there's a very sort of comfortable working cadence, but this architecture really drives us to have a very big battery, but it makes us resilient to the performance of the radioisotope power system. As the plutonium decays, it just takes a little bit longer to charge the battery up, so we could fly a little bit less often. So it's an architecture that really is driven by the Titan environment. Now, the vehicle we ended up with may be pretty ugly as aircraft go, and Mike Kinzel, at whose invitation I'm speaking to you, likes to joke that Dragonfly has all this junk on it, all these drag-causing elements, which are of course the whole reason we're going. The scientific instruments are what the purpose of the mission is. But nobody has ever seen a vehicle like this before, because it's got some really quite unique attributes. I mean, okay, it flies like a rotorcraft, like one of these urban air mobility taxis that are emerging. You've got similar sized sort of rotor blades. Here's a life-size one with the principal investigator of the mission, Zibby Turtle. We have to communicate directly to Earth, so we have to have a dish. It's about 1 meter wide. It's actually not a dish in the parabolic sense. It's actually a flat circular antenna array that we get a 1 or 2 kilobits a second performance to the ground, but obviously we retract that for flight. We have some panoramic cameras that are mounted on the same gimbal as the high gain. The radioisotope power generators at the back. We have drills. Not many aircraft have drills. That's a new one. And drill people like vehicles to be heavy, right? You want to lean on the drill, get a lot of what they call weight on bit, and that's sort of anathema to aircraft practice. And this whole thing has to fly through space to get to where it's going, and so it has to fit inside a heat shield, which is why the front looks ugly and blunt. It's actually driven by the contours of the aeroshell. So there's a lot of very interesting and unusual compromises to be made in putting a vehicle like this together. The mission concept has us arriving at Titan in a hypersonic aeroshell, just like Perseverance is. The mechanics of the Titan atmosphere are such that it takes a couple of hours actually to float down by parachute to the surface, not the 7 minutes of terror on Mars, but 2 hours of mild concern. We'll release from the aeroshell about 1 kilometer above the ground and land under rotor power. So once you go through the exercise of figuring out what you need to soft land on Titan, with hazard avoidance and things like that, then you don't need to add anything to take off and fly somewhere new. That's sort of the beauty of the concept. We have some great animations of this stuff happening at our website, dragonfly.jhuapl.edu. There's a lot of other resources there, some papers, graphics, and movies. In terms of atmospheric flight mechanics, the power to hover, as I said, is sort of 40 times what it would be, 40 times less than what it would be on Earth. It's still several kilowatts, and like any flying thing, there's actually a non-monotonic power versus flight speed curve. When you're in hover, you don't have much drag because you're not moving relative to the air, but the efficiency of the rotors in providing the full set of the full amount of lift is a little bit less than in some cruise condition where you're sort of optimally forcing air into the rotors, and then as you fly even faster still, the drag eventually dominates, and so there's a minimum sort of optimum cruise speed, and this is for an old design, but broadly it's similar. So our optimum flight speed something like 20 miles an hour. And what we'll do after that first landing, and we'll stay on the ground at that site for probably several months actually, and then do a couple of little gingerly hops to check out the flight control system and the navigation and so on. But we should be able to fly for perhaps up to 20 kilometers. I mean, a sort of informal goal when we were formulating this mission was that we should be able to fly further in one flight than any Mars rover has ever driven. And I think technically we could do that if we melt the battery, but with the usual sort of flight rules of land with 50% battery margin, we probably aren't going to quite do that. But what this lets us do actually is fly off from our landing site and scout somewhere new, zap it with a LiDAR, take stereo pictures to measure the topography, and then fly back to where we started from. Because we know it's safe. And then we can downlink that data to the ground and study it in depth over the Titan night, for example, and then decide if that's where we want to go. And if not, we can decide to scout somewhere else. Obviously, the first time we go to B and come back to A, but then we can fly over to C, come back to B because we've already scouted it. And so we can do this sort of 2 steps forward, 1 step back. Scouting, wherein we never commit to landing at somewhere that we're not absolutely happy to go to. The flight mechanics are complex on a vehicle like this, and this is a graphic that I got from Mike Kinzel, who's been doing amazing CFD work, simulating the airflow on the vehicle, the identifying the areas that create the worst drag, like the nose and these pesky science instruments. The interaction between the rotors is actually kind of interesting. At certain flight speeds, the downwash from the forward upper rotor impinges on the rear lower rotor, and that creates some interesting interactions. So that there's a lot to figure out. When we started working with some rotorcraft people, they were actually kind of backward-facing baseball caps kind of tinkerers, and those aren't the people you want for a space mission where you need to be sure that it's going to work when it gets to a new environment. You need that sort of fundamental understanding of the aerodynamics and the aeromechanics, and our colleagues at Penn State and Mike Kinzel at UCF are a big part of that. To be sure that's going to work, you want to check the CFD against physical measurements in a wind tunnel, and we've been doing those in the fall already. That's been a challenge, of course, with the COVID era, and there's restrictions on accessing sites like NASA. These rotor tests were done on a test stand in the 14 by 22 tunnel to look at some of these rotor interactions with the flow at different angles. In fact, the blade section for the rotors is in some respects more typical for wind turbines on Earth. The reason being that the Titan atmosphere is very cold, and that reduces the viscosity of nitrogen. So you in effect get to fly in a cryogenic wind tunnel where the Reynolds number is higher. So that's been an interesting activity in the last few months with its own challenges. Another NASA center, NASA Goddard, provides us the sort of centerpiece instrument for Dragonfly, a mass spectrometer that will analyze the surface material and tell us what it's made of. It's similar to an instrument on Curiosity and on the upcoming ExoMars rover, but with a very wide mass range. I mean, whereas Mars, looking for organics, you're looking for a needle in a haystack. but Titan is drenched in organics, and so we need a pretty advanced instrument to sort of tease them all apart. And so there are gas chromatograph front ends and a laser desorption front end. We can even tease apart with the gas chromatograph the so-called chiral amino acids. Um, they're all, if I always get this wrong, all the amino acids that living things on Earth use are left-handed and the sugars are right-handed, or maybe it's the other way around. They're structurally the same but mirror image of each other, and the fact that they're all one-handedness, if you like, is characteristic of the sort of self-selection that living things do. There are amino acids in meteorites, for example, and they're pretty much 50-50 left and right-handed. So, understand, if we go to Titan and find that there's this enantioselectivity, that everything's one-handed or the other, that would be a very exciting development. That would say that there's been some sort of selection process that doesn't happen on meteorites, for example. Getting the sample into the instrument is an interesting challenge, especially in Titan's cryogenic conditions. It's 94 Kelvin, so motors, need to be heated up. Lubricants, have challenges. We didn't want to use a big heavy arm. We actually have a drill fixed to each skid, and we use a pneumatic transfer system to basically suck the cuttings up into the instrument, and we can use a little valve system to switch from which drill and to which instrument it goes. There's actually a very cool video of this on YouTube that our colleagues at Honeybee Robotics in Pasadena put together. They're a really fun bunch to work with. We've got a full-scale development unit was done in the phase A study before we were selected to fly, in fact, and we tested it in cryogenic conditions and in various kinds of surface material, sticky stuff, frozen ice, frozen ammonia solution, dry powders that are electrostatically clingy. You try to challenge the system in every way you think it might encounter to see at what point it doesn't work. That's a really fun sort of exercise. The drill bit is actually conical, so it won't get stuck, and it just kind of scoops out this pile of cuttings, and the cuttings are sucked away by this sort of vacuum horn. The sample gets trapped in these little cups that get moved to the instrument front end, and the stuff that blows past the cup just gets exhausted through this blower out the side. But as I say, I urge you to have a look at the video on YouTube. It's really kind of fun. We have an instrument to do some reconnaissance of the chemistry before we even commit to sampling the material. There are elements in planetary crusts that emit gamma rays when they're stimulated by neutrons. This has been used at Mars, at asteroids, at the moon. But those bodies rely on cosmic rays to do the excitation. And Titan's atmosphere is so thick that the cosmic rays don't get through to the ground. So we actually have to bring our own neutrons. We use a pulse neutron generator, which is a device used in oil exploration. They lower these things down boreholes and shoot out neutrons and measure the gamma rays that come back, and those are diagnostic of how much hydrogen, how much oxygen, how much carbon, how much magnesium and sulfur is in the surface material, and that information, which we don't need to drill or anything to do, we just sit there and shoot out these neutrons, will help inform whether the stuff is interesting, and we want to drill it at that particular site, because we may visit several dozen sites, maybe as many as 40, and we may not want to drill at all of them. We'll have cameras, of course, cameras looking forward, and these will take images during atmospheric flight as well as sitting on the ground, like these Mars rover images. There's a sort of belly-mounted downward camera, particularly for mapping during flight, but also the downward camera will give us a view of where the drills would be drilling, so we can see the texture of the material. We have a sort of zoom camera, microscopic imager that will be able to image the individual sand grains and inform us what kind of processes have shaped the surface material, and also does it glisten? Does it looks like it's sticky? And we have a couple of panoramic cameras to do stereo and panoramic imaging using the high gain antenna gimbal to pan around. So these will be spectacular images of an entirely new landscape in all kinds of different views. There's a couple of other tricks. At night, when it's mostly dark, there's actually a surprisingly long twilight on Titan because of the scattering in the atmosphere. We can illuminate the area under the lander with some light emitting diodes at different wavelengths, and those give us sort of super color vision that is somewhat compositionally diagnostic. This is actually two different near infrared channels mapped to red and green, and blue light to blue light, more or less. But these different colors are different kind of organic compounds in this ice organic mixture. And many organic compounds, especially those with sort of carbon loops, aromatics, are fluorescent. When you illuminate the scene with ultraviolet light, they glow. You might be familiar if you go to a nightclub with a gin and tonic, because the quinine in the tonic fluoresces under UV and glows blue. And so at night we'll shoot out some UV light and see whether the ground glows, which I think will be kind of fun as well as scientifically interesting. I have some particular responsibility for the DragMet instrument, the geophysics and meteorology package. Will measure the methane humidity, the atmospheric temperature and pressure, the winds, and look for not only minute to minute, hour to hour diurnal variations on the surface, but also will profile these atmospheric properties in the atmosphere by flying up to a few kilometers and back down. We also have some sensors on the skids to determine some of the physical properties of the surface. And we have geophones and a seismometer to look for Titan quakes. And those may help us figure out how deep, how thick the crust is on Titan above the internal water ocean. And in fact, the seismometer is a contribution from the Japanese aerospace agency, JAXA. They had a seismometer developed for a previous mission that we felt would likely work well at the very low temperatures on Titan, and indeed we tested it, and it does. The mission timeline is such that we are planning to a 2027 launch with arrival in the mid-2030s, basically the same latitude and time of year as the Huygens probe, so we can use the Huygens information as sort of ground truth. And then our nominal mission, I think now, is 3.3 years, during which time we'll make probably one flight every month or so, every 2 Titan days. And that will let us cover perhaps a couple of 100 kilometers of forward progress. The area that we're going to with the initial landing ellipse is an area that we know from Cassini data to have sand dunes. These dunes here are about 3 or 4 kilometers apart. And up here is a radar image of Earth, of the Egyptian desert, showing this same sort of linear tapering morphology, and basically the sort of gravel plains and these dunes, which have sharp crests, but have broad flat plinths that are going to be easy to land on, and the area between the dunes should be pretty favorable too. So we're pretty confident that we can find some good safe landing sites to begin with, and then we can scout. Right, we'll want to go more interesting places than just sand dunes, but that's a good safe place to start. taking a bit of a step back, this is our target crater Selk. Basically was in the middle of the map that I showed earlier on. So we'll land down here in the dunes where we are pretty assured of a safe first landing, and then we'll scout and progressively move towards the crater, where other Cassini data suggest that this water-bearing material was thrown out during the impact and may have done some of that that really interesting chemistry that I mentioned earlier. So last couple of slides. What's going on right now? We're in phase B, so refining requirements and doing the detailed design. Also, there's some technology maturation. Early on in the process, for example, the drill system, we tested at low temperature, which we think is the hard thing. Making sure that the drill and the blower work. But to really be certain of the performance, you want to get the Titan temperature and pressure right. The Titan surface pressure is about 1.6 Earth atmospheres. And so we've actually commissioned a dedicated chamber here at APL that, unusually for a space facility, overpressures goes up to 1.6 instead of just down to vacuum. We use gallons and gallons of liquid nitrogen to do this, but we've put in elements such as the shock absorbers, the dampers for the landing system, some of our meteorological instrumentation, and in fact the blower system for the sampling system that was tested just before Christmas. And so there's a lot of testing going on to demonstrate the technical maturity of various elements. I talked about the wind tunnel tests. We have a sort of subscale drone unit for testing some of the autopilot algorithms. Remember, there's no GPS on Titan, so we have to use inertial navigation coupled with vision-based terrain relative navigation, and we've tested those algorithms out, and they work very well. But having a small scale platform is obviously very convenient. This is the sort of testing that's very hard to do on something like the descent stage of a Mars rover, where it's rocket propulsion and so on. But you can take a drone, albeit a lightweight one, on Earth and do a lot of the field testing of many of the hardware elements. So there's a lot going on. We are working towards a launch still some years away, and arrival a decade and a half away. But it's going to be an exciting adventure, and I hope you'll be able to follow along with us via NASA media and our APL website down there. So with that, I'll stop, and we'll see how to deal with questions. Chris, do you want to maybe MC the questions, just read them out to me, or tell me I should look at the chat, or how do you want to do it? That's a great question. In fact, even by terrestrial standards, the Titan winds are actually quite gentle. So 1 meter a second near the surface. We have some measurements from Cassini, from Huygens, that measure just how turbulent it was, and parts of the Huygens descent were what you'd call in terrestrial aviation light turbulence. We intend to do most of our atmospheric flights around 9:30 a.m. local solar time, when the atmosphere will be relatively quiescent. You don't have a lot of convection like as builds up in the afternoon. But the vehicle will take wind readings before it takes off. In fact, there'll be kind of two cycles. We'll take wind readings and look at the weather overnight and send that back to Earth, and we'll make a go, no-go decision on the ground. And then we basically hand it off to the vehicle. And the vehicle will look at the wind sensors itself up to a minute before takeoff. And if it senses that the winds are greater than some threshold that we'll fine tune, but probably 2 meters a second or so, then we'll just veto the flight. Say, looks windy. Let's think about this carefully. So we have that that sort of opportunity to to only fly when we're comfortable with the weather. And we have numerical models, not only at the global scale, but at the sort of landscape scale that are, explicitly looking at, how much does the wind speed up as it goes over the crest of a dune, for example, how the terrain affects the wind. We're building up that capability. So, we're going to be pretty well informed, I think, about the environment. I'm not hearing anything. Is there another question? Sorry.
Yeah, sure. So the next question is it possible that the rotors can dig holes under the drone as it's trying to land, causing its skids to set down at an odd angle?
That's a great question, and I'm actually really interested in that. That was something we looked at very early on. Among my books, you'll notice one about sand dunes. I'm very interested in this problem. One of the key things we want to learn about Titan is exactly at what speed does the sand start to move, because you need to know that in order to be able to decode what the shape of the dunes are telling you about Titan's climate history. And one way we'll do that is by actually firing up like a single rotor at a set of different speeds, and looking with the cameras and some sensors on the skids to detect at what speed the sand starts moving. So that's one of the relatively few ways that Dragonfly actually manipulates the surface material, is with the downwash from the rotors. We have also looked at what's called the brownout phenomenon, wherein the downwash from the rotors kicks up surface dust and makes a dust cloud. There were actually quite a few helicopter accidents in Afghanistan, for example, during military operations there, that were caused because there was a lot of raisable dust in the surface material, and that basically obscures the ground, and the pilots get disoriented, and crashes have occurred. That's arguably less of a concern for an autonomous vehicle, because with the inertial guidance, it knows what level is, at least for the few seconds or tens of seconds coming into land. But we do use a LiDAR to sense our altitude near the ground, and to detect rocks, so we can avoid landing in rocky areas. And potentially the brownout cloud could obscure the ground to that LiDAR interrogation. So we veto the LiDAR below 10 meters altitude, because of the possibility of kicking up dust. So it's definitely something we're paying attention to, and in fact, Mike Kinzel's CFD is really helping us understand the flow field interaction with the ground. So yeah, it's something that's quite unusual for spacecraft to have to worry about, but we're definitely paying attention.
Okay, so the next question is, can you elaborate on the purpose and operation of the gamma ray spectrometers?
Yeah. So its function is to actually there's three elements to it. There is the pulse neutron generator that shoots neutrons out. There's a gamma ray spectrometer which detects the gamma rays emitted by certain elements in the ground. And there's also a couple of neutron detectors. The neutron detectors are particularly good for measuring how much hydrogen there is in the ground. So you could imagine we might land at somewhere that looks dark, like that Huygens image, and that probably means it's carbon rich. But is it carbon like carbon black, all carbon, or is it carbon and nitrogen like some of the material we can make in the lab in Titan simulations? And the gamma ray spectrometer will basically tell us the relative amounts of hydrogen, nitrogen, carbon, oxygen, and some other elements like sodium, sulfur, chlorine. So, is it just carbon-rich sand, or is it mixed with water ice, for example? If it's water ice that may have come up from deep in Titan's interior, is it salty, or is it fresh? Is it doped with ammonia? So it's it's a coarse compositional indication. It only tells us the elemental composition. It doesn't tell us the structure, how the elements are stuck together. But it's very, very complementary to the mass spectrometer in that it gives us this quick reconnaissance. It just takes an hour to accumulate a gamma ray spectrum, and you don't need to drill or anything to do it. So it's very complementary to the other investigation.
Okay, how many RPMs do the rotors spin at, and how does it compare to those to the Earth-based test article?
So the rotor speed is, I think, typically something like 800 RPM. Actually, Mike probably knows more than I do. I don't know what the test article is because that's a smaller rotor. So it's probably faster. I mean, the way to validate a spacecraft design is not to completely replicate everything on Earth, because you just can't, because the gravity's wrong for a start. The approach is very much to have an understanding, a model for how things work, and to calibrate that model with wind tunnel data, with field test data of a lightweight article, a small scale article, whatever it is. But the rotor speed is relatively slow compared to most hobby drones, let's say, because they're small and have quite high rates.
So, how deep are the methane seas on Titan?
That's been a topic of much of my previous work, actually. This is not the best map for it, but it's the only map I've got here. So Dragonfly is destined to go here, Selk, and it's further than we can realistically fly in our nominal mission to visit the seas, which are in winter darkness when Dragonfly arrives, by the way. This sea here, 400 kilometers across, this is a cylindrical projection, so the polar regions are kind of stretched. This sea, Ligeia Mare, is 400 kilometers across, and we actually have Cassini data with its radar pointing downwards that went across here, and that we actually picked up a bottom echo that relies on liquid methane being extremely radio transparent, which is very different from water, of course. And the time at which that echo came back tells us very unambiguously that the depth of Ligeia was about 130 meters. We have another couple of measurements here, and they were, I don't know, 80 meters, 50 meters. We don't actually know how deep the deepest part of Kraken is because we didn't get an echo. Maybe we didn't get an echo because it's actually made of less pure methane. Maybe there's more ethane and hydrogen cyanide and other stuff that's more radar absorbing. So, we just looked into the abyss and didn't see didn't see it come, the echo come back, or it might be that it's actually, you know, 800 meters deep, and again the depth is just so much that the echo is too weak. So we don't know for sure, but probably a few hundred meters. This one we know is 130. So if you look at all this surface area and take the depth into account, there's more liquid methane here by a factor of about 200 than all the liquid hydrocarbon reserves, oil and gas, known on Earth. So it's just sitting there waiting for you to pick up. There's no oxygen to burn it in out of Titan, but you know, that's a separate issue.
So what is a forecasted operating mission lifetime of Dragonfly on Titan?
So the mission duration over which we expect to attain all of our science objectives, to go from our initial landing site and to sorry, jumping forward, I should have quit and gone back in. So go from our landing site and to access some of this impact material, perhaps even in the crater itself. That is set for, I think, 3.3 years. Nothing mechanically happens at that point. The radioisotope thermoelectric generator will be degrading in output by a couple of % a year. Obviously, the longer a mission runs, the more probability that something starts to wear out. We don't have an unlimited number of the little sample cups for the mass spectrometer instrument, but there's absolutely no reason the mission couldn't continue, you know, well beyond the 3.3 years. But you know, as an engineer, you have to figure out the requirement and design to the requirement, and then anything you get beyond that is gravy.
Okay, now I'm going to the chat questions. Are there decisions for landing made by an integrated system on Dragonfly or being made on Earth?
That's a good question. It's sort of a combination of the two. The onboard autonomy is not unsophisticated, but it's not doing any science decisions. So basically, all right, the first landing, basically we come out from under the chute and we won't know exactly where we are. The vehicle will just look for somewhere that's safe. You know, it has a LiDAR on board to sense, you know, slopes and obstacles, and it will just find a spot that doesn't have steep slopes and obstacles, and it'll set down. Then once we're down, we'll have the aerial imaging taken during the flight, and we can take a panorama and look around, and you know, we deliberate on the ground where we might want to go next. So what we would then do is instruct Dragonfly to take off, go over there and scout it, to shoot the ground with the LiDAR, take stereo images, but come back to where we know it's safe, where it originated. Now, when it comes into land, it's using its LiDAR again, and to make sure we don't, you know, put down on a big rock. So the onboard autopilot is basically, you know, just tells it to follow the line, you know, whatever the bearing is that the ground team has instructed or has requested. You know, it has to fight against crosswinds perhaps, and so it, you know, uses inertial guidance supplemented by ground image correlation. But you know, that's not you know, artificial intelligence or anything fancy like that. It's a relatively low level of autonomous flight.
Are we going to be able to see videos from Dragonfly, or is the data flux too low?
I'm certain that we will have some concatenated imagery. I'm sure everyone's going to want to see that. It's definitely true that being you know, 10 times further away from Earth than Mars is, say, and without having relay orbiters, the bandwidth is going to be much less. than you're used to for Mars rovers. But we have 3 years, which is a lot of time to send data down. And one degree of freedom we have is that the energy that we expend in powered flight, we can repurpose, right? We don't fly every Titan day. The sort of nominal plan is we do 1 day on, 1 day off. And during those days when we don't fly, we have a full battery that we can expend the energy sending data back to Earth more often than we would if we were spending a lot of the energy on flight. So there'll be this. I'm sure there'll be a tension between the wish to send more pictures, more data back versus to do more flying. But I could well imagine that the temptation to have some moving pictures will be overpowering, and I think it'll be amazing.
Is vortex ring state a concern? If so, how is it addressed?
They keep asking me the questions that should go to you. Do you want to take that, Mike?
Yeah. We had been looking at that quite a bit. Basically, one of the things that we're finding is that these coaxial rotors are actually less prone to vortex ring state. It's actually, and because of that, we don't feel like it's going to be a concern, and it's only a concern in one point of the flight envelope. And I think that we have so much margin at that point in the flight envelope. It's really, it's kind of been addressed and kind of it's no longer really a concern in the context of it.
Yeah, I mean we've paid attention to it. We've identified the the points in the envelope where those rotor wake interactions could occur, and we'll avoid them. So basically, thou shalt not descend relatively quickly vertically, because then you go through your wake. So the approach to coming to land is a very slow descent, less than a meter per second, whereas the downwash coming out of the rotors is several meters a second. So we've definitely paid attention to that, and as Mike says, the coaxial rotor pairs are more forgiving in that respect than a single rotor would be.
Okay. Do you have any other ideas brewing up in follow-up missions? Maybe a drone in the ocean?
This isn't cool enough for you, really? So that would be actually a really fun mission to put together. I did a little bit of work on some ideas for a Titan submarine, but I think that's some ways away. And in fact, a lot of what you could get from a submarine, you could get from a boat with sort of instrumented depth charges, if you like. But another thing you could imagine and clearly have is a rotorcraft with pontoons, where you could land on land or land on the liquid. The challenge, of course, is never in showing that some particular space vehicle is possible or that it could probably work. The challenge is showing that it definitely will work with no problem. And when you start introducing the degrees of freedom of powered landing on a liquid surface that might have waves, it becomes very difficult to be absolutely certain that you've anticipated all the possible interactions. So again, I think we're some way away from that. Going back to these ideas that came along as soon as Cassini had sort of confronted Titan. There's a lot of things you can do on the ground from a lander. The surface chemistry, the seismology, the meteorological monitoring. There's a set of things you can do from the air. Landscape scale imaging, understanding different aspects of the atmospheric dynamics, and we kind of get that twofer with Dragonfly, right? It's doing the functions, doing the science of a lander, but multiplying it by 20 or 40 landing sites, and we're getting the aerial vistas, but we're not doing the global survey that an orbiter will do. And so there's still very much a scientific need for a follow-on Titan orbiter. And I suspect that would be the next step after Dragonfly, and more exotic surface vehicles, or more Dragonflies. I mean, Dragonfly is going to do just regional exploration around here. There's all kinds of interesting places to explore on Titan. So I think the next step would probably be most appropriately an orbiter, but who knows?
Okay, here's I think we got 2 more questions so far. Is there a concern with brownout clouding the lenses with sand? How is the instrumentation kept clean?
That's an excellent question, and yes, indeed, we have considered that, and in fact, I was actually working on some slides on that earlier today for our internal work on this. What am I looking for? I'm looking for the picture back here. So one point is that the stereo cameras are in this sort of housing that's retracted when the dish is retracted for flight. So the panoramic cameras are protected during flight. The other cameras are all on the belly or forward. So dust lofted into the atmosphere that settles out won't settle on the lenses. Now, you're right, in coming into land, you can kick up material from the surface, and the turbulent recirculation can bring that up to the vehicle. And we've actually been calculating, including using some of Mike Kinzel's CFD results, just how much surface material could be transported. During the phase A study, we developed and tested some dedicated coatings for the camera windows, and there's low surface energy fluorosilane coatings that are very hard to stick to, and by putting an indium tin oxide coating that makes them electrically conductive, that prevents the electrostatic adhesion. So we have a fair degree of protection just from those coatings, and the studies we've done seem to be showing that there should not be significant adhesion of material to the windows, but that's an ongoing study. It's possible to add windshield wipers or covers, but then you have to carry them around, right? An aerial vehicle, you want to be as lightweight as possible, and it's there's multiple apertures that would all need their own covers and need heaters for the motors to drive them, and so you really have to consider very carefully, does the hazard merit that additional protection.
So here's another question. How does planetary protection protocols work on a mission like this?
Great question. So we are working with the Planetary Protection Office at NASA headquarters on defining the formal posture for Dragonfly. But Titan is what is called a, let me get this right, Cat 2 star. There are higher categorizations of locations in the solar system, like areas on Mars that may have water, or Europa, where in principle, if you took a space vehicle that had terrestrial biota on it, they could flourish and thereby disrupt any native ecosystem. Titan is, as far as we can tell, dead. It's of great interest in terms of the origin of life, the chemical steps that may lead up to life, but we have no prior expectation of living things on Titan. If it's life as we know it, then it can only be in the deep interior, under 100 kilometers of ice. So there is no realistic way to introduce material from Dragonfly to that environment. Even the MMRTG isn't powerful enough to melt its way down. Life as we don't know it is going to be operating on a completely different chemistry from terrestrial biota, and terrestrial biota simply can't flourish at 94 Kelvin. So I think the expectation would be that Titan's categorization as 2-star, which is of interest for origins of life but not expected to have life, that just requires analysis to show you're not going to melt through the crust, or deliver terrestrial biota to an environment they could flourish in. And so there's no sterilization required of the vehicle. But as I say, that posture it has to be formally signed off with the NASA headquarters Planetary Protection Office. But it was the case for Huygens. It was the case for other Titan mission studies that this category 2-star applies.
Okay, we got another question. How is the thermal heating from entry compare with MSL, Mars 2020? And is it essentially the same aeroshell utilizing Pika?
Right. I don't know if the thermal protection material is. Oh, it must be, because we talked about that. So the aeroshell shape is actually slightly different from MSL. It's more like the Genesis capsule, and the reason for that is the Titan's atmosphere is mostly nitrogen, not CO2, and I think there's something about the ratio of specific heats and how that maps into the hypersonic stability of a given shape. It has to have the same access to install the MMRTG, on at the launch site, as MSL does. The thermal protection material we plan is Pika, which is obviously been used on past missions. I couldn't tell you off the top of my head what the heat flux is, but it's not. It's comparable with Mars missions. It's not nearly as stressing as, say, the Earth return capsules for Apollo or OSIRIS-REx or Hayabusa. The entry speed at Titan is 6 or 7 kilometers a second, which is comparable with Earth orbit return at Earth or Mars entries.
So I do have one more question.
Mm-hmm.
Where does the name Dragonfly actually come from?
Yeah, we kicked around a number of names. I liked initially proposed Highlander, sort of hybrid lander, but yeah, it's kind of lame. I think Firefly came up at one point, and the idea of the radioisotope power source kind of glowing at the back. But Dragonfly was just a kind of really aesthetically appealing name. And dragonflies, the creatures are really cool. If you look at what they do, at how they hunt, they are really remarkable organisms. There was the idea actually at one point that we might have rotors that were not equal in size, that you'd have an upper plane of big rotors and you'd spin those at a sort of constant speed to provide a sort of sustaining level of lift. And then the lower set might be smaller in diameter, which would make them more responsive. They could spin up and spin down more quickly to sort of fine tune for maneuvering. And dragonfly wings are actually like that. They have slightly different diameters, as reflected in the logo. But dragonfly, everyone just sort of thought, yeah, that's the one to go for.
Yeah, I think it really matches. It kind of looks like a dragonfly too.
Yeah, there's sort of a bit of a hexagonal motif in here that is was supposed to sort of reference, the structure of DNA.
That works. Well, I mean, we had a lot of good feedback. A lot of people can't wait to. We had some people who really like to talk. Others want to show the YouTube video to their high school students, show them how
Awesome.
all the cool things engineers do, and all the cool things you do just individually. It's amazing.
Well, you too, Mike. It's a great adventure, technologically, as well as scientifically, and there's most of the adventure is yet to come.
Can't wait till 2027, right?
Me too. 2034 or whenever. Yeah.
That'll be the big one. All right, I think my audio is back on now. That's good. I do have one last question for you.
Yeah.
Unless anybody else has any more. So, as a mission architect, what is your responsibility with the mission?
Very good question. In fact, I started out as designated as the project scientist, but really what I do is my main activity beyond the leading the DragMet instrument is defining the environments that the engineers need to design to, right? This turbulence spectrum, for example. Sorry, I'm going to flick back here. Yeah. Is this the right description of a changing wind field for the mobility system engineers to design the autopilot to handle? How big should the skids be? How soft is the ground going to be in the sort of worst case soft place? How big are the rocks that we might land near, such that the one skid might be perched on a rock, and does the focus of the camera have to extend beyond that? I get to kind of poke into all the different aspects of the way the vehicle will work, and try to think of ways things could go wrong, so we can fix them in design before we cut metal. So it's it's sort of straddling the realms of science and engineering. I confess it is actually a role we sort of basically made with me in mind. The idea for Dragonfly, as proposed to the NASA New Frontiers competition, arose between myself and Jason Barnes, who is the guy behind this airplane idea, actually. But obviously, it draws on the helicopter ideas I'd had 20 years ago. So I played a central role from the very beginning. Many of the design decisions, like do we have one drill or two drills? Do we have the drills mounted on the skids rather than on an arm? A lot of these decisions we made, even the whole question of, is 4 rotors or 8 rotors the right number? I mean, obviously we draw on technical experts like people like Mike and colleagues from Penn State, but I've been a player in all these sort of major architectural decisions. So yeah, it's kind of the dream job for me. It's a perfect fit for the skill set and experience that I bring, and I think I bring good added value to the project this way.
Great, thank you.
Okay, I'm going to stop sharing.
Thank you so much for the seminar, Ralph. This was really informative, really great. We had a lot of good feedback here, and can't wait again to see how things turn out.
Yeah, thank you very much for the invitation, and let me figure out how to drive again, and let me just put this slide back up for people's benefit. Thank you for attending.
Yeah, thank you very much, Ralph. for anybody that's interested in learning more, definitely check out their website and all the awesome stuff coming up with that mission. I know I'm definitely looking forward to it. We got, what, 6 years to launch, so that'll be in our neck of the woods. So hopefully we'll all get to go outside and see a cool launch. And then there's another 7 years wait, but in the mid 2030s is going to be probably the coolest space mission I think that's been launched so far. Like OSIRIS-REx is pretty neat, bringing back a piece of an asteroid, but at the time that we can fly something on another planet is really a next step, I think, in exploration, because that's kind of what we all dreamed about, right? We're going to be flying around on Mars and stuff, not just taking these little rovers at 2 miles an hour.
Well, don't forget that the Perseverance rover has a small helicopter on it,
That is
Ingenuity.
true.
It's obviously less ambitious than Dragonfly. Mars is a very hard place to do atmospheric flight, but we'll certainly be watching its efforts with great interest.
All right, Rob. Oh, sorry. Go ahead.
Sorry. I was just going to say, yeah, thank you. I think we don't have any further questions right now, so.
All right. Should I disconnect, or do we need to tie anything up after?
No, I think we're good to go.
Ends?
Thank you again for coming in. Thank you, everybody, for joining us tonight.
All right.
Have
Thanks,
a good
everyone.
evening, everybody.
Good night.
Thanks again, Ralph.